a rectangular hyperbola, which is y equals 1 on x. That's try that again. That is an example of a rectangular hyperbola that we have seen before. It's not the only one, of course. Simply any hyperbola whose asymptotes are perpendicular to each other is a rectangular hyperbola. So I guess perpendicular, the vertex in a rectangle being 90 degrees, so that's where it gets its name from. Alright, so what does this mean? We know the two asymptotes will be y equals b on a and y equals minus b on a, or b on a x and minus b on a x. So their slopes multiply together to give -1 because they're perpendicular. So that means b must equal a. Well, that means our equation is x squared on a squared minus y squared on a squared is equal to 1. We multiply by the a squared, and we usually write it in this form: x squared minus y squared equals a squared. So it's sort of like the circle is to the ellipse, because that would be x squared plus y squared equals, well, a squared or radius squared. The rectangular hyperbola is to the hyperbola. So x squared minus y squared equals a squared. Its eccentricity then. Well, now it's not going to be a squared plus b squared on a squared. It's going to be a squared plus a squared on a squared. So every rectangular hyperbola has an eccentricity of the square root of 2. Now, much time can be wasted, and I have seen questions in the past where they ask, what is the eccentricity of this hyperbola? And if you recognise it was a rectangular hyperbola, then you don't have to waste time deriving it. Oh, rectangular hyperbola, square root of 2. So that's its position there. X squared minus y squared is equal to a squared. But we're used to seeing it as something like that, y equals 1 on x. How do we change this hyperbola into one that we're used to seeing? Okay. Well, if those asymptotes are y equals, well, think about it, they've now got to be y equals plus or minus x, because b equals a. So the asymptotes are y equals plus or minus x. If I could rotate the whole thing 45 degrees, then the asymptotes would become the x and y axis. So what I want to do is rotate 45 degrees. Well, back in complex numbers, if we now think of this as an Argand diagram, instead of p just being a point on the hyperbola, let's think of it as a complex number. If I wanted to rotate 45 degrees, then I would multiply by cis 45. So x plus iy, p is now, we're thinking of it as the complex number, x plus iy. I'm going to multiply it by cos 45 plus I sine 45. And both of those are, of course, 1 on root 2. If I expand the whole thing out, there's my expression. X minus y on root 2 plus x plus y on root 2 is equal to I. Now, remember, xy, little x, little y, is referring to the original position of the point. If I now say the new position when it's rotated, well, x must be the real part, so x minus y on root 2. Y must be the imaginary part, x plus y on root 2. When we multiply those two things together, we get x squared minus y squared on 2. But that's little x squared minus little y squared, which was the original equation of the hyperbola, and we said that was equal to a squared. So I've now got x times y is equal to some constant number. And that's what we're used to seeing. Okay, we write it as y equals 1 over x, but I could rearrange that as xy equals a constant number. So, xy equals a squared on 2. Now what's going to be the focus? Because remember, every point has now been rotated 45 degrees. So the focus was AE naught. But remember, eccentricity is the square root of 2, because we're dealing with a rectangular hyperbola. So the original point was the square root of 2a, 0. But again, let's think of that as a complex number. The real part is the square root of 2a, the imaginary part is just 0. we're going to rotate at 45 degrees. So I'll multiply it by 1 on root 2 plus 1 on root 2i, and look what we get. We just get a plus ai. Kind of neat. Rotate at 45 degrees, we just end up at the point AA. So that's going to be our focus. Well, it'll be one of them. The other one symmetrically would be negative A, negative A. Okay, what about the directrix? The original directrix we know is plus or minus A on E, but again, eccentricity is the square root of 2, so we've got A on the square root of 2. So this is now a line that we're rotating 45 degrees. So I've got this vertical line that I'm rotating 45 degrees. So I know my new line would now be parallel to y equals negative x. It was vertical, it was parallel to the y-axis. We're rotating anti-clockwise 45 degrees, so it will now be parallel to the line y equals minus x. Well, if they're parallel, they have the same slope. So the equation must be x plus y plus some constant number is equal to 0. We just got to work out what that constant number is. What else do we know? We know the distance between the two directrices, because back when they're vertical, they had the equation a on root 2. So the distance between the two would be 2a on root 2. So the distance from the origin, I suppose, is more important, because I'm going to use a perpendicular distance formula. So from the origin to the directrix is a on root 2. Now if I rotate the whole thing 45 degrees, and we're rotating about the origin, that distance is not going to change. It's still going to be a on root 2. So I'll use my perpendicular distance formula. I know the distance from the origin to our line x plus y plus some constant over the square root of 2, because remember it's over the square root coefficient of x plus coefficient of y squared, so we get root 2. We know that distance is a root 2. Again, we end up with something really nice. We've just got the absolute value of k is equal to a plus or minus a. So our directrices are simply x plus y plus or minus a is equal to 0. So it works out really nice. But remember, this is when we wrote the equation not as xy equals a constant, it was xy equals a squared on 2. So that's how we work out what a is. So just to summarise that, so if we're now saying our rectangular hyperbola has got x and y axes as the asymptote, we'll think of it in the form not as xy equals a constant, xy equals a half a squared, then that will allow us easily to find a. And once we know what a is, we know the foci will be at plus or minus a plus or minus a. The directrices will be x plus y equals plus or minus a. And the eccentricity is always the square root of 2. Now, the parametric coordinates for it. This time you'll notice, instead of saying half a squared, again, it's just a constant number, I'm calling it c squared. So when we're dealing with parametrics, we call it c squared, because then the parametrics become really easy. We just say, well, x is c times t, y is c divided by t. So when you multiply them together, the t's would cancel, you get c squared. So that parametric form has got nothing to do with the auxiliary angle, like the ellipse and the regular hyperbola did. It's probably more like the parabola. So remember, the parabola didn't talk about an angle, it was just 2at squared. So it's more like that parametric form. The tangent will end up being x plus t squared y equals 2ct. And the normal, beautiful, look at it, whoa. T cubed x minus ty is equal to c outside of t to the power of 4 minus 1. Quarter contact. Because the parametric form is the same as the parabola, if I approach this the same way we did with the parabola, so I could find the equation of the chord PQ. It would end up being x plus PQY equals c p plus q. So I could find that. I could find the point of intersection of the two tangents. And the external point, remember, that's what they would give me. It'll be x0, y0. So x0, y0 would equal the point of intersection of the two tangents ends up being 2cpq on p plus q, and the y value 2c on p plus q. So I, from that, could say, oh, okay, I know x0 is 2cpq on p plus q, y0 is 2c on p plus q, but remember, I want to eliminate the p's and q's. So if I substitute into that equation, pq would equal, just rearranging the first one, p plus q x0 on 2c, but using the second one, p plus q would end up being 2c on y0. So I've now eliminated the p's and q's. That looks a bit messy, but look what happens. We're back to the idea the quarter contact mimics the equation of the hyperbola, if you look at it really closely. Because we said the equation of the hyperbola was xy equals c squared. Well, what have we got? Forget about the zeros there. xy plus xy. 2c squared. So once again, it mimics. That also therefore means the tangent, if I was to write it with Cartesian coordinates rather than parametric coordinates, must be xy1 plus x1y equals 2c squared. It will also mimic the equation. 1991 question. Oh, symmetry. 1991. Gotta love that. Our hyperbola is xy equals 4. First question they said was simply sketch, bit of a gift question I suppose, sketch the hyperbola and show where it intersects the axis of symmetry. So all they're asking us to do is draw a standard rectangular hyperbola. But they wanted some scale, so they've said locate, I guess what we're really doing is finding the vertex of the hyperbola. That'll be on the axis of symmetry. So y equals x. Now if y equals x and x times y equals 4, just in case we're unsure, let's do an equation. That means x squared equals 4, so we know it's at plus or minus 2. So we'll have 2, 2, and minus 2 would be the points of intersection. It then said, alright, let's go and derive the equation of the tangent. So if we have to derive it, find the derivative, minus 4 on x squared. When x equals 2t, we get a slope of minus 1 on t squared. Point slope formula. And rearranging that, we get what they've asked for. So alright, still not too bad, the question. Whoa! So s cannot equal 0. And s squared cannot equal t squared. Show that the tangents of p and q intersect at this point here, m. Don't worry too much about the s can't equal 0 and the s squared. Like, s can't equal 0. Reason? Have a look at the coordinates of q. I mean, if s was equal to 0, you wouldn't have a y value. S squared can't equal t squared. I'm sure we'll find out as we go through this question why that's so. But let's find it. Well, remember, we found the equation at p. We don't re-derive the whole thing for q. We can say, well, when the parameter was t, we ended up with x plus t squared y equals 4t. So logically, when the parameter is s, we must get x plus s squared y equals 4s. Solve them simultaneously. We get t squared minus s squared. Aha! That's why s squared can't equal t squared. Because if s squared was equal to t squared, I would now go and divide by 0, which you can't do. So that's why they've said that bit. Divide, we get some cancelling, and there's the y value, 4 on s plus t, which is what we were looking for. Substitute back in, and we can work out our x value, and we've got the required answer. Okay, so there's m. Suppose that s was equal to negative 1 on t. Show that the locus of m is a straight line through the origin, but not including the origin. So what have we found? We've found coordinates for x and y. It's basically saying find the locus. What links x and y together? But they've given us an additional piece of information. s equals negative 1 on t? Well, if s equals negative 1 on t, I'm not going to worry about the bottom of the fraction. Look what happens on the top of the fraction for x. St is negative 1. So in other words, x is negative 4 on s plus t. X is negative 4 on s plus t. Y is 4 on s plus t. What's the relationship between y and x? So y equals negative x. So we've got the straight line through the origin. But then they've said, but not including the origin. Well, again, have a look at the y coordinate. 4 on s plus t. If I've got a constant on the top of the fraction, that can never equal 0. So we can never get the point 0, 0. So y equals negative x is the line we're looking for. But 4 on s plus t can never equal 0. So therefore I can never end up with the coordinate 0, 0 or the origin. So our locus is y equals negative x excluding the origin. What do you want to do there? Okay. Now, the thing about these locus questions, it specifically says in the syllabus that they will only ever ask locus questions on the rectangular hyperbola. So when it comes to ellipse and hyperbola, they might ask other geometrical property questions, find the equation of the tangent, find the point of those sorts of things, prove that this angle equals that. But when it comes to these sort of locus questions, it'll only ever be on the rectangular hyperbola that they'll do it for.